Hello and welcome to this manufacturing process technology part 2 module 26. I was discussing in the last module about the ECM process, and then today we are supposed to discuss about some additional processes which are directly or indirectly related to mechanical and electrochemical removal, material removal. So the first process which comes to my mind when we talk about such associated processes is the electrochemical drilling. The process is shown in the figure here, right here. There is a tubular electrode which acts as a tool and is normally used as a cathode. The principles behind the process are very much same as ECM, electrochemical machining. Only thing is it is a high aspect ratio drilling that we are executing using the ECM process or electrochemical material removal process. The electrolyte is pumped from the center of the tool and it exists through the side machining gaps. So basically the electrolyte goes in this direction and in this direction, and it is formed between the walls of the tool and the drilled hole. Machining occurs at a high current density in the frontal inter-electrode gap between the tool face and the workpiece. Since electrochemical dissolution acts laterally between the side walls of the tool and the component, so the produced hole diameter will be obviously more or greater than the tool diameter. So you have some kind of gap or tolerance between the final diameter and the tool, even though the tool is insulated or well insulated. So that is what electrochemical drilling is. So CD can be calculated by looking at what is going to be the final workpiece diameter and what is the tool diameter. So CD is basically dW minus dt, and this process produces diameters ranging from about 1 to 20 millimeters. Feed rates are extremely small, varying from 1 to 5 millimeters per minute. For high machining accuracy and smaller diametral oversize, high feed rates are recommended, and under such conditions high removal rates and better surface qualities are also ensured. So you could also have a reverse flow system where the electrolyte is generated from an outside region through these electrolyte chambers, and it goes into the main workspace and goes back through the center channel of the tool. These are normally generated to create the back pressure. The back pressure can be varying from 0.6 to 2 megapascals, and back pressure is normally given to ensure that the total amount of overcut is reduced, or the CD is minimum. So that is how the gap between the final diameter of the workpiece and the tool diameter can be controlled. Also, because of the high pressure, there is a tendency of the gases or the gaseous products which are generated in this region because of the presence of hydrogen, etc., to sort of go out of the machining region without really affecting the machining zone very much, because obviously if the pressure is pressure of infusion of the electrolyte is high, there is a very limited possibility of dissolution of hydrogen that may happen. So the increase in gap pressure, obviously because the hydrogen has been now eliminated, would raise the electrolyte conductivity, and this would enhance the dissolution process. So therefore if you were to plot, there is a directly sort of proportional rise of the MRR if the pressure of the electrolyte feed is increased in the machining zone. The electrolyte back pressure also reduces flow lines in the machine surface. You can see, for example, here the different surface roughnesses which have emanated because of the ECM process, and if you were to operate on a higher pressure, these lines which otherwise come because of the dissolution on the direction of the electrolytic flow would get minimized. The major disadvantage of such a system beside the tooling cost is the increase of hydraulic forces. So they may lead to warping etc. of the tool holding if we wanted to do electrolyte back pressure. Further, the use of proper tool insulation reduces the side machining effects, which in turn would limit the widening of the gap at least over and above the working zone. There is at least a major portion of the tool which is covered or insulated. I think I had given this illustration here. The insulation starts somewhere here in this particular region, and below it is still the tool material. Okay, so it helps to some extent in reducing the overall taper which may otherwise be obtained if there were no insulation. And as such, passivating electrolytes such as sodium nitrate can produce small overcuts which enhances the process accuracy. So overall, we can conclude by saying that in electrochemical drilling processes, the back pressure is of substantial importance, and the electrolyte flow rate may be able to produce a pronounced effect on the overall overcut size, etc. And in fact, if you reverse flow the electrolyte at a certain pressure, it has been found that the CD value or the total overcut value can be minimized quite a bit because of the controlled machining rates that so happen. So the machining current that actually comes up really is a function of the total tool feed rate. If the tool feed rate is high, the machining current would increase sort of proportionally, and there is also a possibility that there may be sparking, because think of it that if the electrode is approaching the workpiece and there at this happens at certain, let's say, advance rate, or let's say some kind of a the rate of gap closure, the electric field also parallelly is increasing. And so if supposing there is a breakdown in the electrolytic media which may happen at a certain small gap value, there can always be at a very minimal gap a spark that is created, and the spark may be damaging as such, and therefore it is always better to avoid such sparks which may be bad for the overall electrical system that is supporting the electrochemical operation. So there is an empirical relation obtained by researchers which has been able to correlate this diametral gap dW minus dt, as I had shown earlier, with respect to the total voltage which is being applied. So this is the electrochemical voltage that is being applied, and the tool feed rate A at which the process of may happen. And so if the A is high, if the tool feed rate is high, so obviously the gap would be higher, because the V to the power of 0.74 minus 0.056 A in that event would be higher, and vice versa. So we must try to optimize the tool feed rate in an electrochemical drilling process. It is a very important parameter to be controlled apart from the overall electrolytic pressure that is existing. So we can also talk about another application of the electrochemical machining, which is about electrochemical grinding. So this is the process again where part of the job is done through mechanical action of the small abrasive grains which are there on the surface, and a major part of the material removal takes place because of electrochemical dissolution. So the electrochemical grinding is a little different from the normal grinding process, which is basically used to produce normally components with good surface finish. So conventional grinding produces components with good surface finish and dimension tolerances, but also such components are associated with some burrs, comparatively larger heat effective zone, maybe some thermal residual stresses which may be always there because of the ill effects of the grinding operation. So one of the main advantages of the ECG or the electrochemical grinding processes is that you have a burr free work surface which is produced because of the way that the material is being removed by partial dissolution and partial mechanical action. So the abrasive action in a ECG process is only about 10% in terms of its contribution to the overall material removal rate. what is more important is the electrochemical dissolution part, which contributes to about 90% of the material removal. And how it happens is again the way that the ECG process is developed and the way that the wheel approaches the workpiece, okay, when such electrochemical grinding is carried out. So obviously the electrolyte also has to be circulated in this case in the ECG process, and hence an effective recirculation system with the supply and filtration needs to be developed. And the commonly used electrolytes are again sodium chloride and sodium nitrate, as have been used in any other electrochemical machining operation as earlier. The ECG process is sort of represented in this figure right here. You have a grinding wheel, as you can see, which is more or less similar to the conventional grinding wheel, except that in this case the material which bonds these grains which are sticking out of the grinding wheel is conducting in nature. Okay, so I can say that the bonding of the abrasive grain is electrically conducting. Electrolyte is normally flown through the IEG, the interelectrode gap, and in this case as you can see, the wheel is rotated in anticlockwise direction with respect to the workpiece, and the height of the abrasive particle protruding outside, this for example is the height that is protruding outside. Bonding material of the wheel helps in maintaining a constant IEG, because the abrasive particles sort of act as spacers. And there are typically 3 zones in such ECG processes. The area in which machining is normally taking place can be divided into a pre-zone, where the pre-zone, which is typically the material removal mechanism in the pre-zone is mostly electrochemical, and the rotation of the wheel helps in, you can say, drawing the electrolyte from this zone 1 into zone 2, where there is a partial mechanical, partial electrochemical dissolution which is taking place. In fact, the advantage of the zone 2 is that whatever deposits have happened in zone 1 because of the dissolution and the material coming out of the electrolyte, and as a result of which the deposit formulates along the surface of the workpiece here in this zone, the mechanical action from the grains which are now touching in the zone 2 may create a carry forward or maybe scratching of the deposited material on the zone 2. So as a result of electrochemical reaction in zone 1, the reaction products including gases contaminate the electrolyte, and that generally reduces the conductivity in zone 2. So there is also a slush deposition to some extent which may increase the conductivity further, and as a result there is a net decrease in the value of conductivity and value of material removal rate in zone 2. However, the abrasive particles in this particular case touch the work surface and start removing the material by abrasive action, while the electrochemistry is going on between the workpiece and the conducting material of the bonded wheel. In fact, what happens is that in the zone 2 there are small cells which are formulated. You could see these closed cells which are packed with electrolyte. Okay, so on one hand the abrasive grain tips or the sharp corners of the grains are sort of grazing on the surface and trying to remove the deposits of the sludge. On the other hand, there is also a dissolution of the sludge into the pocket which is formulated between the wheel and the workpiece. So there's a small part of the material is removed in form of chips, and further the electrolyte is trapped between the abrasive particles on the workpiece surface. It forms a tiny electrolytic cell where small amount of material from the workpiece is electrochemically dissolved. So in zone 2 you can also say that the electrolyte is being forced, because obviously there is a carry forward of all this electrolyte which is pumped in this IEG region, the interelectrode gap from zone 1, and all the residuals also are going to flow in the zone 2. So zone 2, by rotational motion of the wheel, sort of pulls in the electrolyte from zone 1, and there is a tendency of the increase in the local electrolyte pressure in this part of the interelectrode gap. So one thing which is interesting here in this case is that because of a self increase in the pressure value, the dissolution levels of the hydrogen may reduce because it may simply outgas the hydrogen. So it suppresses the formation of the gas bubbles in this gap, and that may result in a higher dissolution rate sometimes in this zone 2. So there is a high dissolution rate, there is also a mechanical action in the zone 2. Also important is the fact that because of the mechanical action, the non-reactive oxide layer which may sometime get deposited here because of sludge from the previous zone, it may promote electrolytic dissolution further by exposing fresh metal to the electrolytic action. So next is zone 3 in the line, and in zone 3 the material is totally removed by electrochemical dissolution obviously, because there is no other contact mechanism or mechanical abrasion mechanism. It starts at a point where the wheel lifts off the work surface. Okay. So typically this particular point here, there is no contact anymore between the grains and the work surface, and there is a sudden depressurization in this particular zone which may lead to the fast carry forward of whatever sludge etc., or whatever pieces of metal the electrochemical dissolution as well as mechanical action may have removed in the zone 1 and zone 2. So in a way it is good that this depressurization may happen at the zone 3 level of a electrochemical grinding process. So that is how this zone contributes to the removal of scratches or burrs that might be formed on the workpiece in zone 3 and also zone 2 and zone 1. So ECG systems are typically more or less similar to what conventional grinding systems have. They have a spindle, they have a wheel, and there is an inter-electrode gap created and an electrolyte flow across the wheel workpiece gap. The machining area normally has to be made out of non-corrosive materials because obviously it should not be degraded electrochemically because of the action of the electrolyte. Power can be supplied through the spindle either with the help of brushes or with mercury coupling, as you can see here in this region. And one good advantage of the whole ECG process is that it has very less chances of short circuiting, because remember there is a mechanical action and there is always a separating grain from the two conducting substrates. So the distance that would be minimum electrode gap, inter-electrode gap, would be dependent on what is the projection height of the various materials sticking out of the conducting surface of the grinding wheel. The other issue is that there may be a possibility of some sparking because there is a moment of time where the gap is too small, but then you have to understand that the wheel rotates, and so the time amount of relaxation time that is given for the spark to build up also is very low in this particular case. So generally it is not needed that there may be any separate short circuiting device. The mechanism of the grinding process itself takes care of this short circuiting, which otherwise may be a very critical issue in normal conventional electrochemical drilling or electrochemical processes, other electrochemical processes. So there are also further several types of ECG processes. For example, you may have form grinding, you may have surface grinding, you may also have internal grinding or cylindrical grinding. So these are the 4 different kind of processes here which is associated with the electrochemical grinding process. Further, the EC cylindrical grinding may be a slowest process because of the limited area of contact between the wheel and the workpiece, whereas the surface grinding may be the fastest among all because of the high contact surface area between the cathode and the anode in this particular case. So that is about electrochemical grinding machine. A little bit details about how the tool is made, or how overall the machine is built up, what is the design. So there is always a tendency of the electrochemical grinding wheel to wear out, because obviously on one hand it is dissociating the or dissolving the workpiece material, but its own conducting holding epoxy or overall the binding material is also getting degraded because of electrochemical dissolution. So there is a uneven wheel wear sometimes which may happen because obviously at one particular point there is more electrochemical dissolution where it is closest to the workpiece. So in order to prevent that, you sometimes need oscillatory motions to be introduced, where the grinding wheel which is in a which is principally having a rotation direction is also translated back and forth over a workpiece surface. So in electrochemical surface grinding the workpiece reciprocates normally. So in internal grinding and form grinding the mechanisms are same as conventional internal and form grinding operations, except that the ECG wheel is conducting and electrolyte is present. The wheels are normally made out of materials like copper, brass, nickel or copper impregnated resins. Again you can dress the wheels in the same manner by using electrochemistry. So in this case there is no mechanical dressing which is needed, the electrochemical dressing may do it all. So in order to prepare or dress them, a reverse current has to be flowed essentially and make the wheel an anode, so that the resolution starts happening from the anode. And you could do this grinding normally on a scrap piece of metal which is unimportant. So what it will do is actually deplete the metal bond and release some of the abrasives, so that one layer is gone and the next layer is again full of projections of untouched grinding material or abrasive grains. So one of the very commonly used abrasive is alumina, maybe grit size of 60 to 80, and unlike the conventional grinding, the ECG wheel may not need much dressing. It may not be frequently dressed because obviously the mechanical action is very low in comparison to the electrochemical action of the particular wheel. So that's about the ECG process. More or less we have covered all the aspects of the process actually. We will now turn to a different process which is actually about electrostream drilling, and in line with that we can talk about a standard electrochemical drilling process to use a hollow metal tube as cathode through which electrolyte flows at a very high velocity. The tube moves in a hole as it is drilled, hence the hole diameter is bigger than the outside diameter of the cathode tube. And in the electrostream drilling, which is another variant of again the electrochemical machining, generally electrically negatively charged high velocity acid electrolyte stream is passed. And the nozzle otherwise is electrically non-conducting, so it is the stream which matters where it falls. The stream strikes the positively charged workpiece, and in the process, because it is already charged negatively, it starts removing the material in the same way as the conventional ECM process does. You can see it here in this particular example. This is actually a case of electrostream drilling. And the main advantage that such drilling process may have is that you can make curved holes or inclined holes, as you can see here. Okay, so you have a sort of a guide which is non-conducting, and it is not an electrode really in this case, but the stream which is being thrown out of negatively charged acid is the one which creates the electrochemical dissolution. Okay, so the dissolved material obviously is flushed out from the machining zone, and this is in forms of metal ions in solutions. There is no sludge to restrict the flow of the electrolyte. Obviously, because it is a stream based drilling, there is some limitation of the minimum diameter of the hole that can be achieved using this process. So typically very small holes and holes which are curved or holes which are at angles which are very steep or even going deep into the workpiece can be realized using the electrostream drilling process. ESD can further be performed in two ways. You could either give a zero feed to the nozzle, or you could provide a finite feed to the nozzle. So if you have no feed given, and typically only the stream which comes out of a nozzle which is at a fixed distance from the workpiece, as you can see here, the process is known as a dwell drilling. And the disadvantage about dwell drilling is that it cannot have a very high aspect ratio structure realized. Normally for less accurate and shallow kind of holes. This is sort of a conventional method which is used. Also, maybe there are circumstances when the workpiece configuration or machining capabilities do not permit the movement of the nozzle. There may be a complex crevice or a cavity in which you are doing the drilling, and there may not be enough space or enough capability for the machine to move the drill in a particular direction. So in those kind of cases, it is the stream which would do the job. One of the examples could be internal cavities, for example, within engineering parts. But the stream itself and the direction of the stream itself would ensure that the hole is drilled in a particular direction. So the nozzle tip is fixed at a predetermined distance from the work surface, and drilling is done by electrolyte stream. Obviously it has limited depth of drilled holes and also limited accuracy. So the second kind of drilling, as is more commonly used in the industry also, is known as the penetration drilling. Just opposite to the dual drilling, you have a nozzle. Nozzle, although is a non-conducting nozzle, it's an insulator, but it is capable of guiding the electrolyte to a zone very close to the workable region between the anode and the stream. So this process, on the contrary, can be used for deep holes. So you can have deep and accurate hole drilling using this particular technique, the penetration drilling technique. So normally it is a wise idea to have a gap sensing device just to monitor the current being drawn, and this can also help you in giving a sort of a closed loop feedback or closed loop control, which can be used for slowing down the feed, and when needed trigger the full power, so that the material removal and the recession of the surface with respect to the point where the electrolyte is emanating, okay, that can be controlled. So this gives you a proper nozzle to workpiece gap, although the nozzle is an insulator here, but if you can monitor the voltage of the stream at the tip of the nozzle, that could be a sort of a basis of a pseudo nozzle, okay, and which could help you in giving a potential gradient between the tip of the insulating nozzle as well as the workpiece surface, and that gradient can be utilized to calculate the gap given a certain feed voltage into the system. So that is another variant of the Electrostream drilling process. I would like to close here in the interest of time today, but then maybe we can take up two more topics in another module where we can talk about that what are the associated processes with the mechanical removal, just as we have seen earlier, abrasive jet machining or ultrasonic machining. There are other processes like abrasive flow finishing, which is a very widely accepted process of industrial grade. So the next endeavor in the next module would be to really look at some of those associated mechanical processes. So in summary, we have done all the electrochemical processes and the sister processes related to electrochemistry, electrochemical removal, and we have modeled the main processes related to the mechanical removal, and we are now looking at the sister processes related to the mechanical non-conventional material removal. So with this I would like to end this particular module. Thank you for being with me. Thank you and goodbye.